I'm sure we can come up with a big list. Okay, so conclusions. Let's talk about what happens to these functions when we do these various things. Now, yesterday, I am fully aware that you could have just plugged each of those functions into your calculator and you could have graphed them. But here's the deal. The way that they're going to ask you questions is in this format. Okay, they're going to ask you, well, what if we do this to the function? How is that going to be reflected in the graph? And you've got to compare the original to the transformation. But they're not always going to give you a function. Okay, they're not going to just come out and say, well, it's x squared, so how does that compare to negative x squared? We'll get into that here in a minute, but I just want to make sure everybody has these conclusions uniform and the same so that we can go from there. All right, we have two different types of transformations. Either you're transforming the x values, which is all the ones on the left side are affecting your x values, which typically result in some kind of horizontal change. All the ones on the right side, well, I have them arranged left and right. Yours aren't left and right. I apologize. All the ones on the right side affect the y values, okay? So f of negative x on the graph, that reflects across the y-axis. Now, don't necessarily erase what you have on your paper because it may be something that we're going to talk about here in a second, okay? Probably should have said that at the very, very beginning, but this reflects across the y-axis. Thank you. I feel like there was something else that I was going to add to that, but I mean, this is the big thing, okay? Or you can look at it as it kind of switches your x values. Your negative values become positive values, your positive values become negative values, but once again, that's just reflecting across the y-axis. Yes, ma'am? Yes, we're comparing. Yes, we're comparing it to just plain f of x. Yeah. Okay. Did anybody come up with any other kind of conclusion yesterday when y'all were going around as to what f of negative x does that you want to share? No? Okay. All right. So, similarly, when the negative is in front of the function, the way that you can look at it is f of x represents y, right? So, negative y is going to take all your y values and change their sign. I don't want to say make them negative, because if they were already negative, you stick a negative in front of it, it becomes positive. So, it changes all their signs. So, this reflects across the x-axis. It reflects across the x-axis. It doesn't really switch any values. It changes the sign of all the y's. Okay, so f of x plus c, when the plus c is with the x, again, that's affecting your x values. So this is a horizontal shift. C units, and it's the opposite direction of what we expect. So what do I mean by that? The opposite direction of what you would expect. What was the shift yesterday that we were doing? It shifted to the left. It was x plus 4, right? I think was the exact transformation. And it moved the graph to the left. We're used to plus being positive. So in the horizontal direction, positive would be to the right. But plus 4 actually moves it to the left. Okay, so plus moves it to the left. A minus moves it to the right, that number of units. Okay, f of x plus c, that's like adding c units to all of your y values. So that is a vertical shift. And since we're adding it to the y values, it's what we expect it to be. So it's c units in the direction we expect. So plus is going to go up, minus is going to go down. Okay, so let's talk about what happens when we multiply our values. When we multiply the c by the x, that is a horizontal stretch or shrink. Or I'm just going to say horizontal change. Okay, and all of our horizontals are kind of the opposite of what we would expect them to be. So just like with the plus and minus before, so here in this case, if c, and I'm going to say the absolute value of c, if it's greater than 1, we would expect multiplying by a number bigger than 1 would stretch things, but it's the opposite of what we expect, so that actually shrinks things. Okay, that is a shrink. And if our c value is between 0 and 1, and I'm saying the absolute value because we can have a negative factored in there as well. We talked about that a second ago. That flips it. Okay, we would expect multiplying by something less than 1 to be a shrink, but it is indeed, in fact, a horizontal stretch. So I think yesterday we had 1/2 x. That actually ended up making it a wider function than it was before. When it's multiplied in front of the function or times the y values, that is a vertical stretch or shrink. Okay, if you ever see a triangle like that in math, that represents delta, which is change. Okay, so vertical change. All our verticals are what we expect. So if c is greater than 1, then that is a vertical stretch. When we multiply the function by 4, it does make it taller. When we multiply the function by 1/2, it does make it shorter. That's a shrink. Now, I don't think that I have the next two on your paper, but you need to add them. Okay, we didn't do them with the graphs yesterday, but let's talk about what would happen if they told us, take your function and apply the absolute value to the x values. What that's going to do is it is going to copy the right side of the graph to the left side. Okay, so you completely ignore the left side of the graph. Okay, you completely ignore the left side of the graph and you copy the right side to the left side. So you keep the right side exactly the way it is and then you mirror image copy it over to the left side. Now here's the reason why, and this is why I had you build those tables yesterday. Because let's just pick a point. For example, I've got a sample graph right here. So say this is my f of x, and I want to graph f of the absolute value of x. So my first point over here is x equals -10. Okay, x equals -10, y equals 2. But if I want to do the absolute value, what's the absolute value of -10? Positive 10. What was f of positive 10? -3. So that ends up copying over here. Okay, so here's what I'm saying is I want to find, let's call the transformation g. I think this will help. Okay, let's say g of x is equal to f of the absolute value of x. Okay, so g of -10 is equal to f of the absolute value of -10. This is f right here. Okay, so the absolute value of negative 10 is positive 10. So f of 10 is negative 3. So that means g of negative 10 is negative 3. So let me put this in green so my colors match. Okay, so I could go through and I could do that for each and every point, but the easier way to do it is just to say, okay, well, there's a line. So mirror image this over here. 1, 2, 3, 4, 2, 4, 5. So that's what ends up going there. And then we get this point right here. And then right here. And then the right side of it stays the same. So this green graph is g of x, which was f of the absolute value of x. Does that kind of make sense? Somewhat. Okay. So what would happen if the absolute value bars weren't around the x? What if they're around the entire function? What do you think is going to happen there? Based on the trends of what's been going on, that's going to affect what values? The x values or the y values? The y values. Okay, so what happens when we put an absolute value bar around something? It makes negative values positive, right? So pretty much what it does is it makes any negative y values. So this one's a little bit easier than the other one, okay? Makes any negative y values positive. Okay, the absolute value of f of x makes any negative y values positive. So pretty much the whole graph is going to stay the same, except anywhere I have negative y values, they're going to, so this part stays the same. I'm moving left from right. Okay, that part stays the same because all those y values are positive. The absolute value of a positive number is still the same positive number. Okay, these negative ones are going to become positive, so they flip over the x-axis. These were already positive, so they stay. These were positive, these were positive, these were positive. And then this part right here is going to flip up. Okay? So that's what the absolute value will do to these functions. All right, let's talk about even and odd functions. Okay, even and odd functions. They were on your paper there. What happens here if a function is even? This relationship exists. F of negative x is equal to f of x. F of negative x is equal to f of x. So what that means, let's throw a graph to this. I think it makes a little bit more sense. Does anybody know an example of an even function? For math 3, maybe? Anybody remember anything? What about x squared? X squared is an even function. So let's think about what this definition says. It says f of negative x is equal to f of x. So for example, f of negative 2 is equal to f of positive 2. Is that true for x squared? Yeah, negative 2 squared is 4, positive 2 squared is 4. Another example of an even function. Thank you. You just set it on the desk right there so I can keep it separate. Preston, right here. Preston. Yeah. Okay. Another even function. The absolute value of x is another even function. Good. No, that's fine. Okay. That's hers. Okay. Gotcha. Thanks. The absolute value of x is also an even function. Okay, think about it. Same thing applies. We can use 2 and negative 2 as an example. The absolute value of negative 2 and the absolute value of positive 2 are the same answer, or have the same answer. Okay, so some properties of even functions. They have symmetry. What kind of symmetry do they have? Over the y-axis. Okay, they have symmetry across the y-axis. The y-axis cuts it in half. The left side's a mirror image of the right side. When you plug negative x into the function, so for example, let me show you algebraically how this works. Let's say my function is f of x equals x squared. So if I'm trying to prove that this is an even function, what I'm going to do is I'm going to plug negative x into that equation. And we know that when we square negative x, that's the same thing as positive x squared. So that equals f of x. F of negative x equals f of x. That's the algebraic side of things for even functions. Okay, so even functions don't have to have an even exponent. Okay, absolute value of x is an example of an even function. Cosine of x is an even function. We could list quite a few in that list, but I'll just stick with x squared, absolute value of x, and cosine of x right now. Okay, odd functions. Can anybody think of an example of an odd function? X cubed, okay. X cubed is an odd function. Any other ideas? How about just y equals x? It's an odd function. Okay, an odd function, when you plug in negative x, you get the negative y value. So, for example, let's use, let's say f of negative 2. We'll stick with the negative 2's here. For an odd function, that's supposed to be equal to negative f of 2. So let's think about that for a second. If our function is x cubed, okay, f of negative 2 would be negative 8. F of 2 would be positive 8, but we stick a negative in front of it. Okay, so that's how that relationship works out there. This has what we call rotational symmetry. Okay, this is symmetry about the origin. It's a little bit harder to see the symmetry here, but it's about the origin. So what that means is if you take your paper and you hold your finger on the origin and you rotate your paper 180 degrees, you'll be looking at the exact same graph. Okay? Or if you look at it upside down, it looks exactly the same as it did right side up. I was expecting to see more heads turn right there, but they didn't. That's what symmetry about the origin is. Okay? So let me show you how this one works out algebraically. If we say, let's stick with x cubed here for a second, f of negative x, when we plug negative x in for x, when we cube a negative number, we know that the result is negative. So see how this is the exact opposite of the original. We stick a negative in front of that original function to get that answer right there. Okay, that's how the algebraic side works out. Okay, another example of an odd function, sine of x is an odd function. Okay, sine of x is an odd function. Cosine's even, sine is odd. Now, most functions are neither even nor odd, to be honest. Most functions are neither even nor odd. So, for example, let me show you, let's take something very closely related to x squared. Let's say our function is x squared plus x. Okay, x squared plus x. Very similar. It's still a parabola. So let's plug negative x into that. When we plug in negative x, we square it, and we add negative x. So when we square the negative x, we get a positive x squared. And then we're adding negative x, so that's the same as subtracting x. So we did not get exactly the same function after we simplified. So it's not even, and it's not the exact opposite. Okay? The second sign is different, but the first sign is the same, so it's not odd either. So this is an example of a function that's neither even nor odd. And if we look at it, if we graphed it, it would not be symmetric about the x-axis. It would not have symmetry about the origin. Okay. So here's what